512 bits, and then do key derivation and storage of those keys. Why is that important? Well, because the unique identifier on a normal chip is not sufficiently different. So they all come from the same wafer, their unique IDs are all inside 10,000 of each other. It'll take you half a day to break that, if not less. So we have to get the cryptographic identifiers right. We have to secure the hard configuration. And with Synergy, this means ensuring that your secure MPU is set up correctly, and also the flash access window, and potentially switching off the JTAG, so we have secured JTAG as part of the Synergy platform. Once we have those components, we can do the secure boot, we can execute through that, we can set up all of our private keys, and once we're happy, once we can make an attestation, a measurement of our platform, then we can launch our trusted software, our RTOS or other trusted software, and then and only then can we trust our data. And without trust with the data, we may as well give up and go home. Okay. So this is a simple diagram of, again, what we were showing out on the floor. And here, for example, we're taking the Synergy devices and we've done some initial personalization. And what we're moving towards with Renesas is that personalization and the injection of the secure kernel happens at the fab. So the birth of the device, we're injecting the keys and all the key material to make that device cryptographically unique. So this is a very strong key set which can't be replicated, can't be guessed. We keep the private key inside the device, and we share the public key through a device certificate. That device certificate is signed by Renesas. We can verify if we want with the OEM which devices, so it can be just any Synergy device, or it's going to be a specific type of device, or it's going to be a specific set of identifiers. We can manage that as relatively simple. And then we can get these into the contract manufacturer, we can bring together the code, we can ensure that only the right number of devices are produced, we can ensure that the code is never exposed. Again, in the example, we showed that we encrypted the code at the OEM, and we only decrypted it in place on the chip. So everything going into the chip was encrypted, the software image and all the key material were encrypted using asymmetric encryption, and they were only decrypted in place on the right chip. And then we can go and delegate ownership to our end user. Delegation of ownership is a massive subject. If you ever want to read a very long essay on it, talk to any of the mobile phone guys and they'll tell you what a pain delegation of ownership is, but it's an important aspect. So how do we enable confidentiality? Well, as I say, confidentiality and cryptography are often mistaken. Cryptography is an important part of confidentiality, it's not the only aspect of it. So, confidentiality is critical to managing privacy of data. We won't get into the aspects of privacy in this conversation. You know, there's a lot of different viewpoints on who owns data and how private it should be, but that's fine. But we have to trust our data if we're going to operate in a big data system. Confidentiality is important, but it is, and passing messages is critically important, but it is only the tip of the iceberg of the cryptographic setup that you have to go to make that message happen. We have to generate public-private keys. Now we can do that, as I say, on the manufacturing line. We have to manage ways of exchanging keys securely. We then may need to cryptographically wrap and store some of those keys. So this is all setting up the channel. We'll then create a symmetric key for the data that we want to pass. We have to encrypt that symmetric key with an asymmetric key before we send it. We have to share it. Perhaps at the far end we need to wrap and store that key because we can't store keys out in the open because that's how systems get broken. And once we have a protected channel and once we have shared the symmetric key, then we can pass some data. So as I say, confidentiality is more than the fact that, hey, I'm going to do some encryption. We have to think about how we want to share data and where we want to share data. So what components do we have in here? I can mention some of these. First of all, we have the TRNG. So this is a very high entropy source. It meets all of the latest specifications. There's a new one coming out, which we think will meet as well, but that's not available yet in terms of the spec. We have a bunch of hash accelerators in there as well, so if we meet the hash function, so we're looking at confirming the packaging of code or of a data packet, then we have the hash acceleration in there. We have symmetric crypto accelerators, so this is obviously all of the AES modes, and I'll talk more about this in the later session, but the AES here is very advanced, so it's not just AES 128, we also cover 196 and 256, and we cover all of the standard modes. If you look at other vendors out there, some of them have some AES engines, but they don't go beyond CBC. The engine that we have in Synergy covers the vast majority of the different ciphers that you'll find with AES. Cover triple DES as well as a number of the stream ciphers RC4 and others. My personal preference is, unless it's for legacy reasons, I would never touch triple DES. It's officially broken. So, but from a legacy perspective, we may need to still connect some devices. So the nice thing about having these accelerators is they allow for that very rapid encryption or decryption of messages, it reduces power. It also reduces complexity because the API that we have to do with Synergy is a lot easier than having to write your own code, and believe me, we've been doing a lot of that recently. And then in terms of the asymmetric crypto acceleration, so this is a piece of hardware, and this includes some primitives for both ECC and RSA. Now, this in a microcontroller is a huge leap forward. So some other microcontrollers allow for symmetric AES encryption, but to my knowledge, there are no other ones out there which have asymmetric cryptographic acceleration. And this is really important because as we move from today's system to more complex systems, we are going to be setting up more asymmetric pairs. In the past, you would install something and you would set up the ECC once, twice, you authenticate it once or twice. In the future, I don't think that's going to be the case anymore. We're going to have to pair more and more devices as we go to multi-vendor systems, zero trust models. We have to presume that we don't trust anything else, and therefore I have to create a secure tunnel to all of these other devices. I don't trust you, I'm going to validate your information. And of course, asymmetric encryption is the key way of doing that. Of course, inside here, there are some other things. There is a unique ID. It's not the cryptographic one, but it's still a large unique ID. We have secure key storage, which is included in the engine here, and some readout protection as well. And we sandwich that between this certifiable root of trust and a software security library with the APIs built into that. So again, why? Well, because the reality is that we are transitioning from monolithic solutions to these multi-vendor systems and solutions with many, many different components in there. Authentication, authorization, and trust are going to become critical issues in those systems. How do I authenticate devices into a network? How do I authorize those? So authorization is often overlooked. It kind of seems the same as authentication, but in a hospital scenario, the janitor shouldn't be able to reset the instrument pump. Yeah, that's the doctors or the nurses. So you have to ensure that you can do authorization as well as authentication. And trust and trustworthiness are important. And Synergy enables that. And we do hit the NSA Suite B level of encryption across the platform here. And this is kind of a high watermark. So this is where, for many years, we were trying to get with mobile phones. As I said earlier, the IoT security is more important than your mobile phone security. It's a far higher likelihood of something going bang. So, the rest of the three, integrity, confidentiality, availability, how do we start dealing with this? Well, as I say, cyber attack is not an if, it's a when. If you don't believe that your device is going to be attacked, you're living in a dream world. It will be attacked. They will find issues. They will find attacks. At some point, you'll probably be out. No matter how good your security is, we're all human. We all make mistakes. We all forget to limit the variables. We all forget to limit the ports. We all forget to limit the debug. Stuff happens. We get better over time, but then the next generation comes through and has the same issues. So, we do see attacks growing. We see the value of attacks growing. We see the number of systems exploding. That's the wrong term there. But there's a lot of wins in there. We presume that something in the trusted network is compromised. Again, this can be your connected light bulb. You know, it's the weakest link in the chain. So we have to have security pervasive throughout our network. My personal belief is I think that security belongs everywhere. If anything is connected, if it has a canvas on it, if it has an Ethernet port on it, if it has Wi-Fi on it, if it has any radio on it, it needs to be secure, because otherwise people are going to attack that node. So the attack may be silent for a very long time. And blacklisting with known compromises is not sufficient on its own. You can't say, well, I know what a bad attack looks like, because these things turn out as a regular knocks. So availability requires isolation of system components, isolation of flaws, and also simplifying of our components so we can properly test and manage each of those components. So I was talking to somebody the other day, and a lot of security is the ability to do pen testing. Awareness of communication, cryptographic measurements of the status, and then very importantly, recovery and remediation. So again, if we make the assumption that we're going to be owned at some point, we have to find a mechanism to isolate the flaw, download an update, make a new package, get rid of the bit which was bad, and update and manage that system over the full life cycle. And again, that can be 20 years. We know with Heartbleed and others. We have a problem with SSL. We have a problem probably with every piece of software that we use. We just don't know it yet. So how do we do that? Well, again, this is where the secure NPU and the flash access window capabilities of Synergy sets it apart. We can use this to create a separate sanctuary where we can have our secure boot, or we can have other critical components of software which are managing the system. This allows us, if something goes wrong in user mode or in supervisor mode, it enables us to identify that something's gone wrong, and it allows us to recover and remediate. So traditionally, ARM-based microcontrollers, they have user mode and supervisor mode, and some RTOSes are built to use supervisor mode, but rarely do in practice. Isolation on microcontrollers, again, in my knowledge, traditionally is pretty bad. Very few people really use the MPUs as they were intended. So job number one, just go and use what you've got there, please. With ThreadX and the FFP, it is built to support the RTOS running in supervisor mode. And that's really important because then we can put our high-level requirements, watchdogs and others in the supervisor mode and our applications in the user mode. As I say, this is not a microprocessor. This does not have a memory management unit, so these, of course, are all inside the monolithic applications. So if you have a variable which isn't constrained properly, okay, well, I can use that to do some form of injection attack, and I can migrate through here. So we have to be careful in how we build these things still. The nice thing is with the secure MPU, this sits apart. You cannot do the injection attack here and force it into the secure MPU domain. So it allows us to separate applications and critical function so that we can then recover and manage our system a lot better. We can reset the device, we can verify the device status, we can manage downloads, and of course we can reflash the device ultimately to remove infected components. I hate to point this out, but again, this was exactly what we showed operating on the show floor the last couple of days, where we were using the secure boot to bring in building a more secure system and what we're trying to achieve beforehand. That's not to say, hey, it's Synergy, you've got some crypto, you're great. You have to understand how you want to use that, how you have to implement that. And I'm probably preaching to the choir when I talk about that. We have to right-size security. If I'm building a cheap device, my security is of necessity different from the security going into a car. That's the reality. But every device, is going to have a level of security. Every device has to be personalized, has to be managed. Cryptography is not sufficient on its own. So we talked to some of the other microcontroller vendors and I say, I've got a really nice shiny crypto engine. Fantastic, that's really good, it's a nice start. But it's not enough on its own. You have to understand the life cycle of the device, the life cycle of the application you're trying to bring through. And then we have to leverage the right tools. So Synergy has security in its DNA. It is in there, it is immutable, it is indistinguishable, it is there from the S1 to the S7. There's the implementation of secure boot information. But the other thing I would say is look to leverage best practice out of other groups. This is a complex science. People live their entire lives doing security. People spend years getting doctorates in security. It's complex and you're not going to learn it overnight. However, there is some help. So I'm on the executive steering committee of a new forum, the IoT Security Forum, which kind of says what it says on the tin. And the group, which is headed up by Imagination, Vodafone, British Telecom in the UK, but it's going global, is all about bringing through best practices. So we know a lot of this stuff in different industries. We know in automotive how to deal with some security. We know in InfoSec how to deal with some security. We know in Mil Aerospace how to deal with some security. People have trailblazed some of these very difficult problems, and we can bring them across. The work that we've done with the secure boot is almost a copy exact of the latest security frameworks for mobile phones. Because that's what myself and my colleague, who was head of security engineering at ARM for the last 5 years, that's our background. So that foundation is there. So in summary, Synergy is going to enable the next generation of security in your applications. We have some great capabilities in there, the asymmetric and symmetric crypto accelerators, that true random number generator is kind of that unsung hero. Without it, the rest of it's no good. You have to have that high level of entropy. We have the hash accelerators, we have secure storage, secure vault capability inside the device. We have to meet all of these challenges, integrity, confidentiality and availability. And we've got to think how the attackers think. We've got to organize, we've got to think about how we recover from a successful attack. Is your system secure against what's coming down the lines? Put yourself in their position. Could you successfully attack your own system? And ultimately, what's the value of an attack? How much will it cost you if something goes wrong? Now that can be liability. If a big oil plant blows up, it can be a problem. I know this myself. So back in the 90s, Piper Alpha, which is a North Sea oil platform, blew up. Killed about 20 people. I was working for a company which did the actuators for the oil pipelines at the time. Now, thankfully, it wasn't our problem. Somebody had taken a big valve out and then routed the oil through an open gap. It blew up. But the cost, theoretically, of a single actuator going wrong on an oil pipeline is incredibly high. Your device may not be so critical. But if it's in medical, what's your liability potentially on that if it's broken? If it's in automotive, we've seen some of the challenges there. Or it may be brand and reputation. If you're a white goods manufacturer and all of your clients' data is suddenly leaked onto the internet, or somebody takes over their heating system in the middle of winter, what cost to your brand, to your value? And that's really the only way to scale security properly. You have to understand the consequences of getting it wrong. We'll never get it right, but you have to understand the consequences of getting it wrong. Okay, so I'm slightly over time. I went very quickly. As I said, that's high level, so apologies for that. So questions? Sorry, over here first.
Assuming you're familiar with DPA, how big a threat is that, and what is Clear to do that?
So the question was DPA, differential power analysis. How big a threat is it, and what does Synergy do there? So a couple of things. I think DPA does have some threats if systems are not created uniquely. I think there are some things which you can do around key rotation, which minimizes some of those problems, but having said that, it's down to your application as to how much you are worried about that sort of thing. In terms of Synergy, the crypto engine, which is in Synergy, was evolved from a platform which was developed for tamper-proof resistance. So I think ultimately, that's a question we'll take offline, but there is capability in there, there is knowledge of DPA and DPA countermeasures built into the crypto engine.
Obviously, the system has good pepper, therefore it's good pickup, and it's advantageous for us, certainly because it's been absolutely based tools. And we pay for that by going project guarantee performance. What, roughly speaking, is that?
That's a very good question, sir, for the camera. The question was really, well, what is the overhead of including all this security in your application? It's actually relatively low for two reasons. First of all, if we do the secure boot first and we engender that integrity in the device, we only have to do that on reset. It's a relatively small amount of code to through that pretty quickly. And then in terms of using the crypto engines, of course, they accelerate the performance of the cryptography. So again, that's not impacting it much versus having to write it all in software. Of course, there is some overhead, there is cost in terms of engineering, there's cost in terms of performance. For a normal application, I would say it would be practically unnoticeable once you got through the secure boot. I don't think it makes a significant difference. With the exception of saying, okay, well, if I am going to send my data securely and I need to set up the ECC or RSA tunnels, then that's going to take some performance. I think it's always worth it. I would, yeah. Because if you get it wrong, you know, the downside of that equation is so much more massive. And I think the other thing I would say is on something like a Cortex M4 running at a couple of 100 megahertz, you've got more than enough performance there. With moving to the advanced process geometries, the amount of memory you have, the frequency, the performance you have in these microcontrollers, it's a huge leap forward over the old ones. So I think overall, your package remains the same, the application remains the same.
I was guessing with the change of CPU, change to Cortex architecture from the previous generation of NSS products, has brought you the CPUs together. The previous architecture can be the crypto came together. Therefore, to some degree, implement something.
So the question again was the bringing together of the ARM CPUs and the bringing together of the crypto. Are these the crypto engine is a Renesas component which has been owned, developed, evolved inside of Renesas. Obviously, bringing forward the next generation ARM platform, the M4, has moved forward things in terms of performance, I think, quite substantially, but I'm kind of biased on that one as well. That was one of my babies. So I think in terms of absolute performance versus previous microprocessors, I would refer you back to the Renesas people in the crowd. I think they can probably answer that one better than I can. So thank you. There's another question.
Your question is,
yeah.
So the question is about the way that technology, and then you really can talk a little bit about basically it's like an attack. Don't track, but then just build anything. So how we can replicate the problem effective and economical.
So again, to repeat the question, with CAN fundamentally has some issues. It was never built to be secure, but there are a whole set of issues evolving in the automotive market at the moment around that, and so how do we secure those? I don't think I can stand at the front, hand on heart, and solve the entire problems for the automotive industry. I'm good, but I wouldn't say I'm that good. But I think the reality is, if you can get the integrity right in the device, then the message you can live with. And of course, in automotive, you switch the car on and off, you can manage the power. So if you can constrain the application which is on the device so that if it's attacked, it's only through that power cycle and then it's lost. If you can do the cryptographic caches on your code package every time you start the car, then at least you can guarantee that the code that you're executing is correct. Now, and you know, in a lot of automotive applications, that's exactly what they do. There's authenticated boot mechanisms already in there. I think we probably need to look at taking those to the next level, and also potentially having other systems which are watching what's going on in the CAN bus and looking for erratic behavior. If you look at high-level gaming systems, I won't call out names, it's exactly what they do. They have an additional processor looking at the main network and looking for unusual behavior. But it's a great conversation to have afterwards. Yes?
Mechanism for tamper detection of automatic destruction.
Okay. So the question there is, mechanisms for tamper detection and automatic key destruction. So in terms of the Synergy devices at the moment, we have to be very careful about the types of threats that we're trying to deal with. Predominantly in this case they are software-oriented attacks as opposed to a full-blown physical attack. So the view taken with Synergy as it stands today is that we're primarily protecting against software attacks. So